Yeah, so hi everyone, my name is Camilo. I'm part of the CARIS lab. So if you don't know, that lab is run by Professor Elizabeth Croft and Professor Mike van der Loos. And we're basically trying to bring robots to human environments, not just keep those in industry, more like bring it and interact with them. And even in industry, we're trying to make it more like an assistant instead of something that is closed in a cage and that you are using it there, right? So the title of my talk today is Towards the Factory of the Future. So that's a big title, and let me try to go through it and try to motivate a bit why we're talking about this. So now, manufacturing in general. So you imagine those factories now that has a lot of robots that are building cars, and they're just building cars all the time. But there are also small companies that actually are more turning in things like that. So there are online and demand purchasing in a global market. There are high product customization and variation, just-in-time production and minimal warehousing, shorter production life cycle, smaller batch sizes. So what you really need is something that you can quickly reconfigure. That is not something that you need actually to make a big setup for make it work. You want something that is flexible. Let me start
as far as
motivating with this
deployment of the initial Baxter. The most difficult process was all the ancillary things prior to fixturing, setting up PLCs, writing ladder logic to get the part to Baxter. And at that point, it was a breeze, because once the part was there to him, the 5 minutes it took to set up a signal and program a move, it was done.
Currently, we have 2 Baxters right now. The first one is set up to run in tandem with another robotic cell, which is taking a part, putting it into a bowl feeder. The bowl feeder loads a robot. The robot grabs the part and puts it into another process which does various machining operations, and then we roll a worm onto the part. And Baxter's currently packing 2 boxes at one time of all the parts that come through that cell, which we produce roughly around 700,000 a year. And then the second area where we have Baxter number 2, we'll call it, he is currently running a milling machine that's auto-fed. Last year we spent about 2,000 man hours on that operation, where this year we're hoping to cut that in half or in third and move the labor to another machine that requires a person to run
it. Okay, so you see now what is happening is that this type of robots are coming to industry. They're very cheap robots in comparison to the big industrial robots. And you can see robots like Baxter. Baxter is built by Rethink Robotics, the same guys that invent the Roomba are the same company, and now they're getting in this market, and actually they're finding market because they need to quickly customize things. They need actually to have humans' ability, and then basically find a way to do that quickly, do that basic programming quickly, and not have to basically deal with the complex industrial robots that you can find these days, right? I want to focus in a particular industrial problem here. So I want to go to a particular case. And this is a collaboration that our lab has with DLR. DLR is like the NASA for Germany. And we're doing collaboration with them. And they're very into building aircraft. So they are basically the ones that build and test things for Airbus and things like that. So it's a very complex task. And one of the tasks that they are dealing with now is that there are some parts, and actually if you see an airplane, an aircraft, around 50% or 60% of their aircraft now is made now by composite materials. The reason of that is because those materials are very light, and they have the same behavior that the strongest steels in these days, right? So the problem with that manufacturing is that this is not something that you can just put in a factory line where you put all the materials and then basically you build all the part and then you have it at the end. It is not working like that. What is happening is that expert has to go there and basically keep an eye on the process, and then depending on what is happening in the process, he has to intervene and then basically change what is happening. So the way this is happening here is there is a big mold. This is part of an aircraft, and this is a big mold that is here. And now what they're doing is laying different layers, basically like textile layers. manually. And then at the end, what they do is bring a big plastic bag. You're gonna see it here, something like this. And then they have to make basically vacuum inside that bag. And then they have to infuse resin. So basically, they start putting that resin inside that. All this procedure is manually. So they basically, the expert here is basically there, laying down, try to figure out how the wrinkles of the bag have to be, just to make sure that that resin is gonna pass in the right way. The only way of doing that now is how you're saying it. What they want to do is actually, they build this nice warehouse where they have a lot of hanging robots on top of the warehouse, and then they want to use those robots to help them doing that. The problem with that is that you're gonna have very big robots near you, and then you need somehow to actually move the robots, tell them to help them doing a specific task. So how you do that? And that's, I guess, what my talk is gonna be about, and what we have been doing towards that goal. Here is a first, show you, small experiment that we did. Just so we want to design all the interaction, but we also design like basically the mechanical part. So this is one of small robots that we have at our lab, and this is basically what the human is supposed to be doing, but the robot is doing it now, right? This is just hard coded, so basically it's just like we just hard code and it's doing. But in reality, what is going to happen is that the expert is seeing that, and then he wants just to tell the robot, okay, go and actually wrinkle in this way the back, or just move the back in this way, in that way. There is not going to be any problem with the resin is injected. So this is hard coded. So now the issue comes, well, okay, we have that, but then we need a good interface to actually interact with the robots, and that's where we actually use AR for doing that. So let me try to walk you through what we have been doing during this past 4 months, I guess. We just jump here. So if you see from the Baxter example, so I guess there are 2 advantages there. First, there is an in situ robot programming. So the way this person programmed the robot is called kinesthetic teaching. So basically, it takes the robot, press a button, and move to a particular place, move the robot to the other place, and then basically record the hard-coded movements, and then the robot is just going to keep repeating whatever he programs, right? That's the advantage of Baxter. And then something that will be interesting to see before actually the robot moves is see how the robot moves in a virtual environment actually before completing the task. So that's the 2 things that we thought at the beginning that will be interesting. And here is our first iteration. So what we're doing here is a simple pick and place task. So we have something that we want to pick, and we just basically want to put it in some place, but we want to do this dynamically. We don't want to hard code the movement, right? We want to actually tell the robot, okay, go there or move there or whatever, right? So what Sarah is wearing here is the HoloLens. I'm not sure how familiar are you with that, but this is a very nice interface, because basically it's augmented reality. The special thing about this is that you're wearing it like glasses Google. So you're seeing your reality, but on top of that, you can build 3D holograms. So that's a very nice thing about the HoloLens. So now what I'm going to try to describe is how we achieve the pick and place task through our interface. The first step is something called spatial understanding. So I'm going to run this video to just show you how this is happening.
Sure.
So she's talking. The first thing that she did, you see that green mesh? This is information that the sensor is getting, basically to have a coarse 3D information about the environment. So if I wear my HoloLens now and I start walking, I can actually build a green mesh on in all tables and on top of you. Then after having that information, I have 3D, basically 3D information to locate, for example, holograms. And that's what she's doing. She basically locates a 3D model of the robot on top of the real robot. So we have a way of actually co-locate the virtual environment on top of the real environment. And then the second step.
Motion plan. Generate.
So there are happening different things here. So she basically co-locate the robot there, and then she, with voice command, define a pick location and a place location. by using just by speech recognition and just basically by moving his head orientation. There is a cursor that is looking the 3D mesh that she creates. Select this for pick and this for place, and then after that she creates, there is a virtual path that appears on top of the real environment. And then after having that,
Edit.
the good thing is that she can actually edit online that path and then have previews of how the movement, you see here is the virtual one, this is the real robot. She's editing the path that the robot actually is gonna be having. And let me just maybe make this video longer. Let's see if I can just quickly go here. Actually, I cannot do it. Okay, no worries. I'll just skip and I'll show you at the end the full video. Okay, so with that in mind, we have three important things. We have collocation of virtual and real world, which is very important. Robot motion preview, so you can actually see how the robot is going to be moving before execution. And then you can also do online programming, meaning that you can change in 3D how the robot is going to be moving. This is important because imagine that you are walking in a factory and then you actually can visualize how all robots are going to be moving even before they start. So you know where you can walk through, you know where to place things, and then even you can correct if there's something wrong online, just directly by seeing the simulations. At the end, just when you feel everything is all right, then you just execute the task command, and then everything is going to start moving. Okay, let me keep showing you more things. So here's actually, you see, we have the virtual model, the real robot at the same time moving, grasping the object, and then just basically
Continue.
following the path.
Continue.
And then just dropping in the set location, which is that virtual sphere that you see.
Reset.
So we identified two main challenges here when we finished this first prototype. Was basically the registration between the virtual world and the real world. That's very hard because even the HoloLens is very good on located itself, but it's not good enough for industry. So we need more precision in industry, right? So that's what we're looking there. This is quickly how the things are working. So we have like a lot of things happening here in the HoloLens side, and in the other side we use something called ROS, which is stands for Robot Operating System, which is like a communication layer that now roboticists are basically using a lot, and it's even moving to industry. So everything is open source, so it's very nice just to maybe take a look to that if you're interested. Two things about the real world registration. So you saw spatial mapping. So what it has, the HoloLens, is basically a small Kinect, use the same technology. And with that, you can get things like that. So basically, I'm mapping now part of the lab. And you can use some type of semantic in the sense that you can try to find floors, you can try to find walls. Here, for example, the code, what it's doing, I map a lot, and they say, okay, find the space in the floor where I can actually place my robot. And this is what it's doing. And then I can move around, I can just observe my model, see where it is. And you can imagine all the possibilities there. So that's one way of doing the registration, and we're working on that. The other way is we're also exploring this, which is basically the common air tags. We already integrate that with the HoloLens. So basically, this is the camera that is in the head of the HoloLens, and this is what you're seeing actually. So you're going to see a vivid 3D model basically on top of the thing. And with this, we're planning actually to do a better registration of the models in the industrial setting. Now let me keep going. I'm going to skip this. It's just maybe much. Okay, so now what's the next step? So we have like the motion plan, but now we actually want to go and try to help the person that actually was doing the bagging pleating. That's how we call the process. So we start by just importing, actually let me just maybe run this one. Importing the model. So you see now like basically a 3D model of one of those molds. And then what I'm doing here is, by using my orientation of my head, I'm building here, you see this red thing here is a cursor that is actually just, when I move my head, it's just gonna be there. And then what is happening there is that I'm selecting different points on top of that 3D model. Based on that geometry, I'm finding basically where are those points with respect to the robot, and then I'm also calculating the normal based on the surface, and based on that I can just plan the robot to just be there in a normal orientation or whatever. So I can basically precisely, at least, put the robot, you see here is the orientation, it's exactly the same thing that is doing the virtual world. The problem is, again, the calibration between the virtual world and the real world. But here is a big issue for roboticists. And the problem is that all that you have seen, it's been on the air, right? The problem comes when you take the robot and actually you go and touch things. Why? Because you need to be very precise. All the controllers in the robot is basically, let's say that here is my robot and I want to, let's say I want just to pick up this. So I send my robot. If I teach, it's not going to be a problem. But then if I'm relying on an external sensor, what is going to happen is that if the sensor is not well calibrated, instead of picking, I may just end here. And he may not know. And what is going to happen, this robot has a lot of strength, right? What is going to happen is going to start going, and maybe it's going to damage the piece, or it's just going to hit something. If I want to go and touch the table, let's say I based on my input of the sensor, I go there, but there is going to be maybe a small, let's say 5 millimeters, 3 millimeters of error, and it could be that then I'm not touching, or then I'm touching too much in the sense that I could break the table. So then we start thinking, okay, we need actually to have something more like human behavior. So that's called compliance. So that's how actually we move our arm. So when I'm going to pick this, I normally move, and here the stiffness of my arm is very high. But when I get here, it actually turns very soft. So I'm changing the stiffness of how my muscles act. When I move here, I'm moving very fast, and I go very slowly. And that's the same principle that we're going to use in our setup. And we start doing this type of experiments. So holograms, the holograms that you're seeing, you can interact with them just by seeing. You can maybe hear from the HoloLens, but now how you can touch the hologram. If you really want to touch the hologram, how you're going to touch it. So a way of touching the holograms is actually using a robotic device. So what we did was we programmed the robot in a way that actually he knows the surface of the hologram. And then what is happening here is that every time that I want to reach to the hologram, basically builds a field of force. So actually I can feel the surface of that hologram. So I can go with the robot and then feel the virtual surface. And I can do that with different surfaces. You see, I'm trying to get inside, but there is like a virtual sphere that is controlling there that is not allowing me to get inside. So I can actually feel the holograms through the robot. The reason why we did that is because actually we want to start experimenting with two things: touching things and also feeling holograms. So we have, you see here, we have like a virtual cube, we have a virtual sphere that actually we can just go there and touch it and feel it. So now we can hear, we can see the holograms and we can touch it, which is very important. And the next step, just don't see those equations. The next step is this one. So this is the idea. I'm here, I have a copy of my robot there, and then here is the cursor that I'm using to set my path. Right? That imagine that you're now in that big mold, and then you're standing outside of the mold, and then instead of you going and do the wrinkle process, what you do is you see the robot and you tell, okay, robot, I need that you go to that location and start doing that. And the way I'm doing this now is I'm looking at a specific part of the model, and then I'm going to start, can I see here?
Set point.
Yeah, just set point.
Set point.
And this
Set
will
point.
just start setting initial points. And this information that I'm using here is the one that I'm going to use to lock the robot in that location. But I'm going to lock it,
Close menu.
not in the very strong way. I'm going to lock it with compliance, the thing that we talked. So you see, I'm just touching here the robot, and it just moves smoothly. But it's actually locked to that path. So if I try to go outside of the path, I cannot go. The other thing that I have here is a Mayo. You know, the Mayo device. Are you familiar with that? So basically what it's doing is just reading the electricity in my muscles. and then just converting that to a signal. So now I can imagine the person just walking around the mold and then just setting the path and then just moving the robot through the path just by waving his hand. And this is very intuitive for the person. Then you can just remove the robot and then just set another path and then just start again if you want.
Set.
So what's next? So the idea is, okay, you saw that in a plane, right? But now we want to move to the actual mold and everything. So the next idea, and this is like more the futuristic idea. So now we have, remember the big mold? We want to overlay on top of that 3D model based on maybe markers. You have here the markers. Here is the operator, the yellow guy. And then he's wearing the HoloLens, right? And then the idea is that as soon as you put the HoloLens, then you have that mold just overlaying on top of that virtual model, or on top of the real model. And then what we're going to do is just remove the model. It's going to be there, but we're just going to hide it in such a way, because what we want is that actually they can see the wrinkles in the plastic bag, because it's going to be changing. Why you cannot just do this with a Kinect or with another vision sensor? The problem with that is that it's translucent, and there is a lot of problem with translucent things with lasers, Kinect, I guess any depth sensor in general. So the reason why we want to do that is we have the 3D model, we basically hide the 3D model, but it's still there. So what we're gonna hide is the 3D model, but he's also seeing the wrinkles in the back, the changing back. And then at the end, he's just basically gonna specify the path. He's gonna send one of those big robots that that I showed you before, hanging in the warehouse, and then he's gonna finish the task. Things that are interesting to explore here is, so remember Baxter, the robot that is getting in the market now, and the industrial, they're basically using that. The way they're programming Baxter is just, they're taking Baxter and they just move the robot and teach basically the movement, and then the robot just replicate the thing, right? A second step is how I show you with the virtual path specification just outside. A third version will be, you're actually doing the kinesthetic teaching, but you are also seeing points projected in space while you're moving. So besides, it's kind of what I show you with the feeling the surface, but here you're gonna be able to see the path where the robot is moving, and then if you want to change it, you can actually change it and have previews of how the robot is moving. And yeah, and I guess you can expand that as much as you can. I'm not gonna get into details of these ideas, but it's the same concept. We have actually two WAMRs in our lab. So one thing that we're thinking is basically have teleoperation between those two, and then on top of that, add the HoloLens and see how we can make more immersive the experience. Yeah, and that's all. I don't know if you have questions.
We have time for maybe 2 or 3 questions.
You mentioned teaching the robots through mimicry.
Yeah, it's called kinesthetic, yeah.
But how are you going to map the human joints and human movements into the robot, because it's not one-to-one?
No, that's not what is happening there. So they use that normally in industry. They just take the end effector, so basically the end part of the robot, right? Mm-hmm. And they just put it in a mode which is called gravity compensation, which is basically, for us it's easy to hold our hand, but for a robot, holding the arm, and then just hold enough to be able to do this, that I kept pushing, and he's just gonna hold in the position where is my hand, is very hard. So there is a mode, a control mode of putting the robot in that situation, and then what you do is you have like a free, you can take the end effector is the tip of the robot. You can just basically move the robot. So what people do in industry in these new robots is they take that tip, but they're not basically mapping the human. They're basically taking the end effector. They're moving the robot here. Let's say that I want to pick this. This is the robot. They move the robot here. They press a button. Here is picking. Now put this here, and then they release. And then what they're doing is replay all the time this. Yeah. In our case, what we want to do is this more dynamically, and actually a person doing that. If you want to do what you're saying, there are ways of doing that. There are like exoskeletons. So you can just attach a robot basically to your hand and then just replicate the movement. But those are very expensive, and still there are a lot of issues with that. Yeah.
Other questions? Yeah.
Thanks very much. It's a fascinating presentation. I just wanted to ask, it looks like right now you're relying on the internal model of the robot to verify its own location. Are you working on using the spatial understanding system or a supplementary scanning system to verify that? And it seems like redundancy is a big part of what you're trying to achieve.
Yeah, there are a lot of issues there with basically with calibration. And no, we're using the spatial mapping. So if you saw at the beginning, actually the way we're here. So when we do this spatial understanding, if you see here, here is the grid, right? And here you may not see that, but here is the cursor. So what Sarah is doing is seeing at a particular point of the robot, and based on that position, she's locating there the hologram of the robot.
Yeah, I understand you're geolocating the robot.
Yeah,
using
exactly.
the mesh. I'm wondering if you're using like a finer grain of scanning to confirm the
No, so we have that problem, and then what we're thinking is maybe using also air markers for doing that, but it's still that calibration problem is still a big issue. Like we're just going around that. So yeah, that's a big problem that we have actually to deal at some point. In our particular case, in the industrial application, we are solving that in two ways. The first way is actually giving compliance to the robot. So basically, when we send the robot, we actually don't care that there is like 5 millimeters offset, because actually the compliance is dealing with that. Yeah. So even if there is gonna pass the command, then it's just gonna easily, like it's gonna work like a spring. So it's just gonna stop there. Yeah, that's the way we're trying. Yeah, exactly. Yeah.
Thank you.
Yeah.
We should probably start wrapping up, but I want to say thank you.
Yeah,
Camille.
sure.
Yeah, please give it up for Camille.